Okay, so this is not rotational energy, but instead it is torque that we're going to talk about. Hopefully an idea that is familiar and comfortable to you, but in case it is not, a brief refresher that I have a rod. It has a pivot point that it is turning around, and torque then would be the turning force. And the turning force on this rod, or indeed on either of these doors being pulled upon by these mysterious disembodied arms, the amount of turning force that you get depends upon how much force you apply, but it also depends upon where you apply it. I hope you looked at these two and you could tell in which case I would get more torque for the same force, and that would be the one where I apply it further away. That it turns out that the torque that you have depends upon how much force you apply, and it depends upon how far away from the pivot that force is applied. It's going to be directly proportional to the amount of force, directly proportional to the distance away, but it turns out it is only the quantity of the force that acts perpendicular to the arm that produces turning force. The component of the force, I'm about to run out of room, so we'll have a short component here. This component of the force does not cause any turning around that pivot point. Only this component causes the turning, and so we have this result that the torque is equal to the arm times the force. These are both vector quantities. This goes from the pivot out to where the force acts, and of course force is a vector quantity, but the torque that we get is going to be a vector quantity, so we need to do a vector product, or a cross product, which is RF sine theta. But after all, what does that sine theta give you but the perpendicular component of F? And so in this picture you can see the arm and the force. This would be the angle between them. You would pick up R and put it with its tail at the tail of F, and when they are tail to tail, that is the angle between them, the theta. And if you take the sine of theta, you get this component here, which they've drawn back here, and that's the one that does the torquing. Here is an alternative where instead of taking a component of the force, they've taken a component of the arm. Well, that's just a commutation here. Instead of R times F sine theta, they're doing F times R sine theta, and here's that same theta, and R sine theta would be this perpendicular component, that is the component of R perpendicular to F. I don't like this. I'm not in the habit of using it, but engineers like it a lot, and they give a name to this force. They call this the line of action, and this is called the moment arm of that F, where the word moment is used whenever whenever distance matters. It's not just F, but how far away F is that matters. We will talk about the moment of inertia, and it matters not how much mass you have, but how far away that mass is. And so the word moment is used. It has nothing to do with time. It always refers to how far away you are from the axis matters. We speak of a moment. Okay, so hopefully that review of torque is enough, and you are ready to do this checkpoint where you have these four forces and you're to rank them according to the magnitude of the torque that they produce, greatest first. Do it and then come along with me. Here is a problem where we will work with torque. That we have a mass hanging on a cord, and that cord is wrapped around a disc, and the disc will be caused to turn as this mass falls and it pulls on the cord. Okay, you may be ready to do this. What I want to know is what acceleration the block will have, what acceleration the disc will have, and what the tension in the cord will be. And perhaps you're feeling your oats. We did problems like this last year. And it might, if you're feeling your oats, it would be very good for you to run with your oats. Stop the show and do the problem to answer these 3 questions. But if you like a more comfortable approach, I would take you through it step by step. In either case, I want you to do it and show your work there on the worksheet. So, what we need to do first is get a free body. You knew that, didn't you? We'll have the weight of this yellow block, and we will have the tension in the cord acting on the yellow block. That tension is the same throughout the cord, so it also acts up here on the disc. There are no other forces acting on that disc. It does have an axle, but I'm going to ignore the normal force from that axle. And we are going to complete our free body, the yellow box is going to accelerate downwards, and there's going to be rotational acceleration up here, but that rotational inertia will equal the linear acceleration of this point on the rim. And can you figure out, do I multiply or divide? Wait a minute, this is radians per second squared, that's meters per second squared. I've got to divide. And so the acceleration that this box has is going to be the same as the acceleration that this end of the string has. It's going to be the same acceleration that that point on the wheel has. It's going to pull without slipping, and so we can get from alpha to A. And they are the same A up here and down here. All right, now I've identified all the forces and the accelerations. I, of course, go to Newton's second, and if you stop the show and are starting it up again, I hope you feel chagrin if you did not go to an explicit statement of Newton's second. I will do it both rotationally and translationally. Translationally, you have the torque is causing the rotational inertia to have acceleration, and of course I can convert so it's the same A. If we look here, we have the weight in the same direction as that presumed acceleration, and the tension going contrary to it, causing that mass of 1.2 to have an acceleration A. And here we have the radius crossed with the tension, same tension you had over here, causes this rotational inertia. We said this was a disk. You may or may not recall, but you really do need to start recalling that for a disk the rotational inertia is 1/2 the mass times the radius squared. And here for alpha, I'm going to put in A over R. You need to be careful that these are the same R's if you're going to write them both as R's. Well, the weight I can get from this and the acceleration due to gravity. And so I have these two equations with T and A unknown. And over here, they gave me a value to put in for R all over the place. And this M would be this mass up here, not the 1.2, but the 2.5. And again, an equation with T and A. So I could solve these two equations simultaneously and get the acceleration of the block, and then take that and divide it by R and get the angular acceleration of the disk. and then plug back into one of these two equations, probably this one is easier to work with, and get the tension in the cord. And we will compare our results when we get back together. This is a problem of great challenge, and you should not take it too lightly. Listen carefully to all I have to say. That what we're ultimately going to be trying to do in this problem is to find out how fast this object, it is a ring with a rod welded onto it that is pivoted about this diameter of the ring, and it's going to be let go. It's going to swing down through an arc, and I want to know how fast it is going as it swings through its lowest point. There we have finally gotten to rotational energy, the promised topic of this lecture, but probably this is the most important slide. First, we need to get the rotational inertia of this object. And you can go ahead and do that, and then go ahead and do this part here, and stop the show and do it, or listen to me, assuming you're not fed up with my voice. Rotational inertia. I need to treat this as two objects coupled together. The ring about its diameter, I don't happen to know, but I would go back to those tables that we have and look up that value. Then you have the rod. You want to add that on to the rotational inertia of the ring about rotating about a diameter. And there's nothing cheap about this. You've got to do a parallel axis theorem. You do a rod, which I do remember. That's 1/12 m times the length of the rod squared, and the length of the rod is 2r. And then you need to do a parallel axis theorem. You need to add on to the rotational inertia about the center of mass the fact that I have moved the center of mass 2r away from this axis. Adding the rotational inertia of this rod in its displaced position and of this ring together gets you the rotational inertia of this whole lollipop. Now, once you've got that rotational inertia, you're ready to do the angular speed as it swings through its lowest point. This is the thing that it is so important that you follow me as I work with this. You cannot do this problem in terms of the kinematics formulas. You can't get the final velocity using v final squared is equal to v initial squared plus 2a delta x, because the a, or the alpha if you like, is constantly changing. The force on this rod will change from orientation to orientation as it swings. The torque on the rod is going to change. You cannot use those formulas, and so I hope it is immediately obvious that what you ought to turn to is energy. And I hope, if you did it on your own, that what you wrote is, I'm going to do this problem in terms of energy. And it looks like this. Mr. Houghton's nuttiness. Write it. And then you need to consider, what sort of energy do I have at the beginning? And I hope you could fill in that with the fact that you have gravitational energy at the beginning. The thing is up in the air. When it has gotten to the bottom, I'm going to choose that as my zero height when it's at the bottom, and so there will be no gravitational energy at the bottom. It will have rotational kinetic energy. And it is from that rotational kinetic energy that I'm going to get the speed it is moving at. Notice I do not add on a term for translational kinetic energy. If this axis for the object is fixed, then there is not translational kinetic energy when I deal with this object as a whole. Now, if you wanted to deal with each of the little pieces of this object and work out the kinetic energy of each of those little pieces and add them up, you could say that the gravitational energy becomes kinetic energy. But it is much nicer to treat this as one object, work with that rotational inertia, which we saw a long time ago comes out of adding up all the kinetic energies, and this is the only energy you have. Fixed axis, no translational kinetic energy. We will ultimately do problems where you do not have a fixed axis and you will have translational as well as rotational, but not yet. Now, this is M, G, H. But that H needs to be how far the center of mass has fallen. Key idea. The change in the center of mass is what you want to put in here as H. The center of mass, these both have the same mass. So this has a center of mass right here. This has a center of mass right here. So the center of mass of the two of them together is right there. It is R above the axis. And where will it be as it swings through its lower point? R below the axis. So for H, I'm going to put in 2R. Because that's how far the center of mass falls. Folks, get this right, you're going to be happy campers. For the rotational kinetic energy, I will use that value for I that you derived at the beginning of this problem times omega squared. And you can see I can solve for omega in terms of M and R, which is what they gave me. And then once I've gotten omega, I can get to V by multiplying omega by R. So do that. Be happy and come to class. Bye-bye.